Okay, Math 12 students, before we move on to the last section of Chapter 4, I just want to go back and cover a few loose ends from Section 4.5. So the first thing I want to mention is that if given an exponential equation, there are actually two ways to solve the problem. There I go again, not knowing how to spell. Two ways to solve. It really just depends on how you look at it. So, suppose you have something like, 2 to the x minus 3 is equal to, 5 or something. Well, one way to solve it is just to use the definition of a logarithm, right? If you recall the definition of the logarithm over here, I'll just put in a little cloud bubble over here. The definition of the logarithm is that if a to the x is equal to y, then x is equal to log a, base a of y. That's just the basic definition of what a logarithm means. So some folks just look at this equation and they say, okay, the base is a, our exponent is x minus 3, which is like the x over here, and the 5 is like the y. So by using the definition, you can just immediately rewrite it, x minus 3 equals log base 2 of 5. So you just get that in one clean step if you happen to just be invoking the definition. And since you need to solve for x, you have x minus 3. The rest of the problem, I think, is pretty straightforward. You're just going to add 3 to both sides. Here's another reason why we use the parentheses around the 5 to remind us that these are unlike terms. And so this is our solution. And I've already explained how to put this into the calculator if you need to get a decimal approximation for that. So I'm not going to do that today. So that's one way to do it. That's by definition. But there is another way. The other way is more of a mechanical way. The mechanical way has its advantages in that you don't really have to take this leap here. Oftentimes when you go from this problem and you jump right to the logarithm, students immediately get confused. They're like, how did you get that so quickly? So a mechanical way to do it is to look at the base and take the logarithm of both sides. And again, I say this is kind of like a square root problem. If you were taking the square root of both sides, you would get, square root of the left side, square root of the right side, or something like that. So this is analogous to taking the square root of both sides, but of course it's not a square root, it's a logarithm, but it's the same basic idea that you're applying something to both sides. So it gives us the idea of balance. It goes back to our original education in algebra, where whatever you do to the left side, you do the same thing to the right-hand side. And so some students find this mechanical method a little bit easier. If you do it the mechanical way, though, you have several steps before you even get to this step that we got in the definition. So it does also have its disadvantages. So now we have log base 2 of 2 to the x minus 3 is log base 2 of 5. You bring the x minus 3 down to the front using the property of logarithms. You know that log base 2 of 2 is 1. So now you have x minus 3 times 1. And so doing it the mechanical way, look how many steps you have before you get to the step that we were able to get in one step using the definition. We got in 1, 2, 3, maybe 3.5 or 4 steps to get to this point here. Either way, you should get exactly the same solution. Adding 3 to both sides, and we should get the same solution, which we do. So I encourage you to try it both ways. Try using the definition and see if you can take that leap. If that confuses you or if that causes you to make a mistake or get the wrong answer, then do it step by step. I'll also give you a little tip for the step-by-step method. Some of these steps are a little bit redundant. For example, going from this step to this step does not really take an additional step. You could save a step there. And then oftentimes what students will do is at this point just cross off the log base 2. And on the left-hand side, that basically jumps you right to this step. So you can streamline it a little bit so that you don't have to do it in 5 or 6 steps. You could maybe do it in 1 or 2 steps. Okay? So you have choices. And I encourage you to make both choices. Decide for yourself which one you like better. Okay. Well, there's a few other loose ends I want to tie up. The next one is very similar to that. If you were to solve a logarithmic equation, when you're solving a logarithmic equation, suppose we have something like this. Well, again, it's the same idea. You're going to have 2 ways to do it. You have 2 ways to go. One is you can go by definition. And again, it's the same definition as before. If log base A of x is equal to y, then x is equal to a to the y. So this is a common log, so the base is 10, and so by definition we would immediately get the equation x plus 4 is 10 squared. You see, the x plus 4 is the argument. That's our x in this definition here. The 2 is the value of y. The y value is 2 here. So we have a to the y is 10 squared. And that gives you the answer relatively quickly. X plus 4 is 100, so x is 96. And again, that technique sometimes confuses people because if you write this equation down on the board and then in the very next line you write x plus 4 equals 10 squared, sometimes the mind goes, who? You know, how did you get that so quickly? So keep that in mind, that there is an underlying definition that sort of is happening behind the scenes. Or you can do it mechanical. You have the mechanical method, which is really a step-by-step algorithm, or step-by-step procedure. So what do? We take the log, we identify the base. If you don't see a base, you assume it's a 10. You apply the 10 to both sides. So you apply the base to both sides. You use the property of logarithms that says same base, same logarithm, cancels out. You get x plus 4 equals 10 squared. It brings you to the same equation that we got by using the definition, and you should get exactly the same result. So either way, your choice. You have two different ways to solve the equation, and you should get the same result either way. All right, so that's my comment from the last couple lectures that I want to make sure is clear before we move on to the next section, especially before I post the next quiz. Hint. Next, I want to talk about restrictions on the domain and the range. Let's start with an exponential equation. Suppose I want to solve something like this. So we have a natural exponential function, e to the x plus 2 is equal to negative 3. So remember, an exponential function, the domain, that's the x values, is all real numbers. So there are no restrictions on what x can be. All right. X can be anything. However, the range, it's the right-hand side. This is basically acting like y. The range is 0 to infinity. So one way to keep that in mind is if you drew the graph, e to the x plus 2 would essentially be a graph that is the e to the x graph shifted to the left. It sort of looks like, let's see, at negative 2, the y value would be 1. So it would sort of look like this. I'm not being very precise with it. At 0, the y value would be e squared, which whatever e squared happens to be. If we plugged in 0 for x, a little table of x's and y's. E squared is about 7, right? 7.4. So that's about where that point would be. 7.4. So again, x is free. X is free variable. The domain is negative infinity to infinity. It can go all the way over here to negative infinity, all the way to positive infinity. There is no restriction on the value of x. However, look at the value of y. The value of y must be greater than 0. So down here we have negative 3. And at no point does this graph ever intersect the line y equals negative 3. So even if you were to try to solve this equation, you know what's going to happen. You're going to get no solution. So if this occurs, put does not exist, DNE, there is no solution. You can see this mechanically. It's one of the nice things about the mechanical process is sometimes you don't notice things, and so you just start driving. Put the pedal to the metal, as they say, and see what happens. So you do it mechanically, just like we were discussing in the last example. We have a natural exponential, so natural exponential uses the natural logarithm. Of course, that's done intentionally. The natural logarithm would cancel with the exponential. We get x plus 2 equals ln of negative 3. You might think everything is going great. Oh, everything looks good. I got an answer here, right? X is equal to ln of negative 3 minus 2. Oh, everything looks good, right? Try to enter that and see what happens. All right, let's see. You want to know if something works? Try it to find out. Error. error, error. So clearly, the natural logarithm does not allow a negative argument. Remember, the argument must be greater than 0. Yeah. So if you don't catch it on your first attempt and you accidentally give a solution to something that has no solution, when you go to actually evaluate your solution, you're going to find out that your solution is nonsense. It just does not make any sense whatsoever. So keep that in mind. When you're doing your homework or your quiz, you'll see a few problems sprinkled around where if you don't notice it, you might end up wasting 5 or 10 minutes on a problem that actually has no solution. So hopefully that'll save you a little bit of time. Well, if this type of restriction happens with an exponential function, the same thing should happen with a logarithm. So suppose I have log base 7 x plus 3 plus log base 7 of x minus 3 equals 1. So this time, the domain is restricted. The domain is restricted. Both arguments must be greater than 0. So we cannot have a solution that's less than 0. We cannot have an x that causes the argument to be less than 0. So we can do a little scratch work here. X plus 3 must be greater than 0. So that means x must be greater than negative 3. And x minus 3 must be greater than 0. So x must be greater than 3. Both of these must be true. Both of these must be true at the same time. So if you look at a number line, or simply just look at the x-axis, you've got 3, and you've got over here negative 3. In order for both of these to be true at the same time, it must be greater than 3. So this is your domain. X must be greater than 3. So being greater than negative 3 is not sufficient. It must be greater than 3. Well, let's go ahead and solve it and see. So getting back to the equation at hand, we have the sum to product rule. So we can rewrite this sum as the product of the arguments. Don't forget your base 7. You can multiply those now just to get it over with, have there be less parentheses. This is a special product, so that comes out to be x squared minus 9. You can do this mechanically, or you can do it by definition. How about we try remembering the definition? By definition, if log base 7 of x squared minus 9 is equal to 1, then that means x squared minus 9 is equal to 7 to the first power. Or in other words, x squared minus 9 is just 7. You could solve this pretty easily. Just move the 7 over. X squared minus 16 is equal to 0. This looks like it's pretty factorable. It's one of those special factorizations. X minus 4, x plus 4. These are our candidates. X equals 4. X equals negative 4. Check with your domain. Only one of these solutions is in the domain. Only x equals 4 is a solution. So x equals negative 4 is called extraneous. In other words, it's outside of the domain. Okay, so hopefully that clarifies a few things for you. I wouldn't say that these examples are common. They're very uncommon, but they do appear out of nowhere. You'll be going through your assignment, and all of a sudden you'll come across a problem like this, and I want you to be aware of it if and when it occurs. So I'll be on my office hours today at noon. So go ahead and log in to Canvas, check the link, and if you have any questions, I can help you with that. We'll be having our quiz on this tomorrow. I'll post it. I'll give you the weekend to get it done. So hopefully that was helpful to you all.